So yeah, we utilize an array of collections. We ask for an element out of an input. That was weird. Am I still sharing my screen?
Yeah, you're good.
You went
Okay,
to the
I just-
void.
Yeah, I just disappeared for a second there. Anyway, but yeah, when we solve it, we're talking about complexity when we're dealing with an array or a hash map or anything that we can jump straight to the item by just giving it an item. No matter how big that array is, no matter how big that hash map is, that set is, if we give it the index or we give it the key, we get that item instantly because we just jump to that spot in memory. It's an O of 1. We talk about linear time or O of n. That means for every input, we have an equal number of increase in our time. So for every one input, our processing increases by a certain amount. So when I double my input, I double the amount of processing time it's going to take. That makes sense? So if I have twice as many items, it'll take twice as long to do it. That's fine. That's normal. That's considered fine. The worst system, of course, is exponential growth, which looks like this. It curves up and out. And what's the problem with that one? What do you see? What's the problem with this at some point?
At some point, it reaches like infinite.
Yeah, you can't really add any more input because you're never going to solve it. It's just too much to solve with any sort of human time frame. That we can't handle.
Or is that stack overflow?
Usually that'll happen, yeah. Usually if this is happening, then eventually, yeah, your system's just going to run out of memory most likely or something. But again, this is time complexity, so not necessarily. As long as you're not using memory, you're just running a lot of processes. It'll keep going, and your computer will just chug.
Oh, I see how recursion can do that. I see that.
Yep. Yeah, what you're talking about when you see a stack overflow is an exponential memory growth or exponential space complexity. So time complexity, that just means that eventually your algorithm just will not solve in human time frame. Think of this as if you were trying to output or print to the console every type of permutation a deck of cards can have. It just will not happen in human. Even if you started trying to print it at the start of human life, when the first human was identified as a human, there wouldn't have been enough time in the existence of mankind to even run that. Even if a computer was printing out a different permutation every millisecond. That's how many different permutations there are for a deck of cards. It's insane.
Is it the one that goes up? Is that also would be an infinite loop also?
You could argue that, yeah. Oh yeah, an infinite loop would just, it's just infinite time. There's no time that it'll take. It just goes on forever. What we have on the other hand, wait, I think I got these backwards actually. Yeah, that means infinite input. I put these backwards. I am having a day today. This is going wonderful today. Time.
So that would result in a runtime error, right?
Again, not necessarily. A computer will continue to process something until you tell it to stop. Because programs on your computer are running until you stop them, or until again something causes it to crash. Usually a space complexity, time memory, like if the time runs out, or if it's not responding. So if you have your algorithm, so in this case, yes, it might cause that because during that chugging, the system won't be telling the computer anything, or will be giving updates to the operating system, and that's what you might see during this computer is not where's this right. Again, we'll go back. I know a lot of you guys several of you play games, but even with programs, if you run a program or run a game and when it's booting up, you see them not responding, but if you wait, it eventually starts responding again. Mm-hmm. That's kind of the concept that's happening with this system. The time complexity is so high that it's taking forever. It's not telling the OS to go. It'll keep doing it as long as you let it, but eventually the OS is going to be like, hey, I'm not getting responses from this device. It might not be doing anything, even though it technically is. Even though we know that application is booting up, it's running, it is doing something, because it's processing so much and just dealing with time complexity, it's not telling the OS, hey, I'm doing something, because it's in the middle of it. It's in the middle of doing something. And so it's really just computers looking at your program. The program is going like, they're staring at it with a blank face and drool dripping out of its mouth as it just thinks aggressively about the universe.
I mean, if you like old basic, if you did a one print hello and then two go back to one, it's not going to computate anything. It's just going to continue to print forever,
Yeah.
and it'll never crash because it's just printing. It doesn't. It's not doing any work.
Yeah. And again, this is the difference of like the input size. This is an algorithm that if I was just to give it like if I was again to give it, so you talk about the permutations of trying to print all the permutations of a deck of cards. If I was just to give it a set of 5 cards, it would run. It would take a little while to print them all out, but it would print all the permutations of 5 cards. Right, a deck of 5 cards, ace, 2, 3, 4, 5. How many different permutations can I have with no suits? Mm-hmm. So how many permutations can you have of that? Not a lot. So that will run and it will output perfectly fine. But the idea when I give it 52, it will run. And if I never stop it, it will eventually do the output, but it's going to take forever. And it's going to take longer than human history will take to print all that out.
So the way you have it on your graph, though, you say like from the letter E to like almost where the letter M is, that would work fine. But then if you did 52, you'd be all the way up top of that line.
You'd be off the chart. Yeah.
Okay.
Yeah. Number permutations, a deck of cards, 52 factorial. There you go.
Oh, Jesus Christ.
My head ran out of memory trying to read that number.
So when people try to tell you that every time you shuffle and deal a deck of cards, that permutation has never been seen before in the universe, most likely, they are not kidding.
Yeah, but the thing is with shuffling is it isn't truly random. So
yeah, so there is a chance you could end up with the previously done one, but the odds are so rare that it is very likely that you have created a never before seen permutation. So
you want to look at a lot of permutations of something like a Rubik's Cube.
Really?
Oh yeah, there's a lot.
Oh, I believe it. That makes sense.
Because it's a 3x3x3.
Oh God.
I've got a 5
That is big.
by 5.
I have to compare these two now, side by side. Hold on. Where do I have something I can write down? I can paste this in. That will be fine. Hold on.
It probably isn't as large, but I still think it's really fun. Because that's the one that
annotation should be able to do a text.
There you go, right there.
Is that just colored plastic, Mike, or can you take the stickers off on that?
Take the stickers off.
Oh, he had one.
Oh, he's a 5x5 one too.
Yeah, he's got a monster. Because the only way I could do those is if I pulled the stickers off.
Here, let's grab this
that
guy.
definitely is a lot bigger.
Yeah, I was gonna say, I think the deck of cards is still more complicated because
Mike, you're muted if you want to talk.
Because
was it
My bad.
9 yes.
I said the stickers will fall off if you try to do that.
So I think
before I actually learned how to do it, I would take it apart with a screwdriver and then just pop it back together. But that would make it fall apart too.
That's I'm very curious what the calculation for a Rubik's Cube permutation is because it's a 9 by 9.
Well, it's a 3x3x3.
Oh, right, 3x3x3. That's it.
I used to do that.
So it'd be like a 27 factorial, maybe. I don't know.
27. Yep. So it's about half of a deck of cards.
Yeah.
So still a lot, but yeah, it's. Look at the difference of that. Look at the difference right there.
Easier to read as well.
Yeah. I just want to point this. I just want to see this very quickly here. Look at the number. Look at the difference between 27 factorial and 52 factorial.
It doesn't, in my head, it shouldn't be that big of a difference, but it's massive.
Like when you go into like exponents and other shit, like the difference between each and every number is massive.
Yeah.
I know that in theory, but looking at it and knowing the concept are two very different things.
Yes. That's the thing about exponential growth. We as humans, it's hard for us to understand or see that because we don't experience that in our life. We don't experience exponential growth, really. We experience exponential reduction because as our life expands, as we live longer, every year is smaller and smaller for our life. Like your 32nd year on this earth is 30 seconds, is so small compared to like your first year of life. The first year of life is 100% of your life. Your 32nd year is 32% of your year or something like that.
Well, that's relativity, isn't it?
Yeah, which relatively relates similar to exponential growth and stuff like that. But it's not. It's something you can't really understand and comprehend.
Get into a Pink Floyd song over here.
So that's one of the exponential growth. Over time, if of a exponential growth algorithm over time has a cap. There's a limit to what it can handle. And that's why exponential growth algorithms are considered the worst. That is O of n to some sort of x. Anything of this. The higher this x, the worse. So that's the main thing you want to keep in mind there. The higher that x, the worse your algorithm is. The next, so if you want to think about it, what's the better solution? We have this one versus this one. What would be better? We want to know what the opposite of exponential growth is.
Is it log n?
Logarithmic growth.
Oh, logarithmic. Okay.
Logarithmic growth. Logarithmic, as you can see, now goes this way. At some point, we don't care how much input we put in, it's not going to change the time. At some point, as we can just start shoving tons of data into it, but it's still going to take about the same amount of time to solve it. My biggest example of this, and I've told this before, so always keep this in the back of your head. Again, I know this is a little dated. Freddie probably doesn't understand this concept, but phone books. Like we take a phone book, we have a book of numbers and stuff like that. Poor Freddie, everyone's down like laughing. But we have a phone book, we need to find a name in it. Our first instance to solve that is to do what? We need to find a name in the book.
Right in the middle of the book.
Yeah, we go right to the middle. So we have a data set this big of all the names. We go right to the middle, and then what do? That's not the middle, but whatever.
Rather go up alphabetically or down alphabetically.
We need to go from there.
Yeah. If where we are is alphabetically lower than what we're trying to find, we will then check this side of the book. If where we're looking is lower in the alphabet, we'll check this side of the book. And what we do is we end up cutting out half the data in a single step. So in a single step, we knock out half the data. We do the same thing. We go to the middle, we decide again, we cut out half the data. We go to the middle again, we cut out half the data. And so if I was to take this data set right here, and I was to actually double it and add the exact same amount of data in there, how many steps have I just added?
One.
My algorithm. Right, exactly. So for all we know, this data set could be 2 million records. I just added another 2 million data points to my data, yet I only added a single step. And that's where you're seeing this end of the exponential growth system. As I start to add more, and that means again, so here I added 2 million, but then the next time I had 4 million on top, and I still only add a single step. And after that, 8 million to add a single step. Then I need 16 million to add a single step, and so on and so on and so on. That is the idea of exponential growth. Eventually, we are adding massive amounts of data and only adding a single step to our algorithm. And that's why logarithmic growth is considered one of the optimal solutions other than constant time. Sound good? So again, you'll hear more about this during the challenge. He's going to talk about that kind of stuff in the algorithm, in the course. So that, where's that? What screen? Here here we are. Yep. So the second one here, he's going to give you a slightly better solution. So he's going to review, sorry. In this one, he's going to review the brute force solution, probably the exponential growth solution. At the end of it, though, he's going to give you a hint on how to think differently about the problem that could hint to the next better solution, to a more efficient solution, to maybe a linear time solution. And so he's going to give you a hint of some way of how to think about the problem, how to think about the data and think about the problem slightly different to see if you can think about that better solution. So then challenge yourself, see if you can come up with that better solution. If not, it's fine. But he's going to go ahead and then on this one, he's going to review that solution with you, go over that solution and give you the final hint to find the optimal solution to this problem. He's going to give you one final hint on how to come up with the final optimal solution, potentially a log of n solution of some kind, some sort of logarithmic solution or constant time solution. And then again, they'll walk through it here. What I really like again is that he doesn't just walk through the code, but walks through the thought process and how he evaluates and how he can consider it and how he comes up with it. My goal for this problem, of course, is to give you guys multiple exposures for every single problem. You get multiple exposures of multiple different ways to approach a problem and solving it so that you can use these for future problems moving forward. And that hopefully one of these approaches might click with you so you can learn how you can try using that for your algorithm going forward. That you might help you learn how to approach, analyze, and evaluate problems. Make sense? Mm-hmm. What we're going to do over the weekend, or for next Tuesday. So for next Tuesday is algorithm day. On Thursday, we're doing more Spring Boot. So for the week, I'm challenging you guys, based on the time frame here, to finish time complexity for Tuesday. I think it's doable. So it's about a total of an hour. If you go for both the introduction and the time complexity section, it's just 2 algorithms. You guys have enough time to work on that. I think that can be done. So we want to have these done for next Tuesday. That sound good? At least that. Of course, you go forward, I'm not going to stop you. Feel free to do more, but you should at least have these 2 done. As you move forward, you'll see we get into arrays, counting, which is something that can take a long time. Here's a good one here. Take a look at that. Stacks and queues. We've done that before. So if you are struggling with stacks and queues, there is a stacks and queues section. And I don't think he does get into linked lists, unfortunately, but he does get into a lot of things that you'll benefit from. So the main thing, again, is this is just that idea of approaching a problem from a logical standpoint, from a computational standpoint, without code, and then writing the code. And this is in Java, so you'll be able to follow along with the code as he writes the solutions to the algorithms. You'll be able to code along with them, write along with them, and attempt to solve them with them. Any questions on this?
How do we get these videos?
Oh, they're in the classroom and they're material. Classwork.
I don't see.
Java
see
material.
that in there either.
I didn't
Not
see.
in the I see the post, but not the actual.
I forgot the link, didn't I?
Yes.
Thank you.
Sometimes
Nope,
that.
that's my number. That it does. Save. I said attach a link. I don't want you adding the file. I've done this before. Like, no. I'll attach it. Oop, that's done. There. So I'm going to test that link, make sure it works. Make sure again you're in your career devs account. It won't work with your personal. So.
Put in preview file, you may be offline. Download it.
Download the file.
No. 2.2 gigs.
What?
Downloading.
It's saying, it said, did everybody get that? Couldn't preview file?
Yeah.
It's
Can't
asking
preview it.
you
No,
to
it's a
download
zip
it.
file. Yeah, it's a zip file. You have to download it.
Oh,
And
yeah.
then extract it. Yeah. Yep. It is a Udemy course, but we downloaded it and compacted it for you guys. Yeah, you can't use the Udemy account.
0.2 gigs. Oh man, my internet's gonna die.
That's why, again, yeah, don't download it during class. Wait till after class, please. And that's why we compress and package it. So.
Your time and complexity is going to crap out.
Download anyway. Dude.
I would say probably you might want to wait till after class to download because it is a large file and it could slow down your internet for what you're doing with Zoom, you know? So again, Sergio probably has a gaming computer, so he's probably fine.
Well, I mean, gaming computer, not gaming internet, right?
Why wouldn't you have both? I do so much with programming. I do have the highest level internet from Verizon right now. So I know I don't use it. My computer has like 300 down, 300 up on a regular basis.
I didn't even know.
And that's-
You already downloaded, so it's gotta be fast.
Yeah,
Developer,
mine's
you don't know
already
the
done.
speed of your internet?
I
Come on, none of these things. You should be curious.
know every little detail about my PC.
I have the cheapest plan Cox will sell me.
www.speedtest.com. Test your speed.
Well, that's because the only reason I'm able to afford the fastest internet is because I have a cheap cellular plan because I don't really use my cellular phone right now because of COVID. I decided to lower that down. I used to have a better plan, but I don't need it right now. I just sit at home all day on my internet. I don't pay for electricity or any utilities in my apartment. So like the only utility I use on a regular basis is the internet. Like that is the utility I use probably 20 hours a day. So, and the wife of course uses it for her stuff too. So like if there's anything I'm going to spend my money on, it's the internet. I don't do cable or anything like that. Yep. So like I'm going to splurge on the internet.
Makes sense.
It's the thing I use the most. And because of you guys, I'm usually downloading a couple of these like video tutorials to review myself. I don't want to be sitting here for 2 days to download something like that just to confirm and see if I like it or not.
Plus,
also
you
don't
need
want
to
to be sitting
upload
there.
your YouTube videos.
That too. I also got to upload, and yeah, I don't want to be sitting there for like an hour and a half waiting for those things to upload, or 3 hours. So the benefit of Verizon over Cox is that Verizon has 300 down and 300 up. So my upload speed is just as fast as my download speed. Cox Communications, yeah, they'll give you like a couple hundred down, but then they'll give you like 10 megabytes up. Their
Wait,
up
you
speed
just
is
said
abysmal.
you just said you had the highest speed at 3.
Well, that's what my computer can handle. The
Oh,
computer is
okay.
maxed out at 3. The router itself can handle 1,000 down, 1,000 up.
Yeah.
So the router, that's why.
It needs a gigabit
Yeah.
connector.
Yep. So like my wife can be doing the exact same thing using her computer full on with like her online games and stuff like that and watching a video. I can be watching a video while downloading and not see any on my phone while downloading and not see any loss on my laptop. My laptop will have 300 megabytes per second to itself. My wife can probably do 200 megabytes per second because her computer's a little old. And my phone probably does like 150 to 200 megabytes a second.
I think I got the slowest in my my computer streams pretty well on my phone wherever I'm out and about. I have my own personal Spotify.
The main thing for me is that just because if one of the devices in my network starts doing something crazy, because the computer has a max download speed, it won't affect the other systems. It's like, you guys don't know, I have another computer right over here that's doing stuff as well. So, so I have a lot of
3 computers doing
devices
at once.
So a lot of devices. I got so many things going on when I'm not in class. So it's all good though. It's all fun. It's all interesting. So anyway, that should be there. It should work. Again, I'll recommend you guys download it after class so you don't lose your internet. But if you have a good internet, go for it. So again, what I want to do today, just kind of wrap it up. We only have a couple minutes. Again, I want to kind of introduce the concept of binary trees, and we're just going to create the node and an add to tree method today. That's it. Nice and simple. It's quick. So you guys can get into these videos. I want you guys to go watch these videos. At least try to get through the introduction and the first problem tonight. At least be introduced to it. I think you guys can squeeze that in, unless you have a super early day tomorrow for work. But I think you can squeeze it in. Let's do it. IntelliJ. Let's get that open. Here it is. Cool.
Jury duty tomorrow. Ooh.
Oof.
Fun.
That's good.
Exciting.
Right now, they're guilty. Save you the
That's
time.
what I was going to say. I was going to say guilty. I was going to say they should be, if they were in court. Why would they be in court if they're not guilty? Or I should just do the Steve Martin joke, death penalty for popping tickets.
Jim, how many times have you been accused of doing illegal stuff on your computers now?
Yeah, exactly. Oh,
but he is
I just
guilty.
got another one of those the other day when I downloaded the South Park.
True, he is guilty. But I'm saying if he went to court with someone thinking that from the get-go, he'd be screwed.
I'll take the other end on this joke then. Jim, remember, it only takes one to hang a jury.
That's right.
Jury nullification is a real thing.
So I can either do that, or I could just say I wasn't paying attention to court. I wasn't paying attention. I'll just go with you guys.
Oh God.
Jeez, you
The
ruin
only
our
thing
system.
about it is I don't have to go to my
Absolute state
job,
of the legal
and that's
system in this
good.
country.
I don't mind being there.
There's our justice system for
Yeah.
it. The industrial prison complex.
Well, as long as I don't have to go to work, that's all I really care about.
The modern mentality of the criminal justice system. When we first introduced the concept of trial by jury, people were like, "This is revolutionary. It's awesome. It's the best thing ever." And they were like, "It's a waste of my time," because it kind of is. That's just because we don't value the workers. We put their jobs at risk. The jurors.
And they don't pay you well enough either.
That's it. One, you put your job at risk because you're not at work, and two, they don't pay you enough to actually be willing to actually be able to do it. If you do it for long enough, you're going to start running behind on bills. Like, we never pay anything enough. We pay the things we don't need, and we don't pay the things we do need.
I did ask him if I could bring my laptop so I could like do some coding and stuff. He goes, "Oh yeah, you can if you have time." I'm like, "Oh, okay."
I'm surprised by that, but all right. I totally thought they'd be like, no, because you can't be exposed to the outside world.
It depends if they're going to sequester you or not.
That's the term. I forgot about that. Yeah, they don't always sequester you. You're right. Yeah, they
Unless
sequester
you're
you.
dealing with unless you're dealing with a Manson tier case, they're probably not going to.
No, it's just
Gotcha.
not federal court. It's just regular court. So I'm not really. It's regular state court. So
Right.
I don't know what it is.
All right. Let's get back to this. I just realized that's all on video now. It's all good.
I forgot about that.
Jim's unwillingness to actually participate in the legal justice system legitimately is now recorded and permanently on camera.
Oh no, he's an average human. We have proof now.
I know.
This might be the one video we decide to edit before we post.
Maybe. Anyway, package. Let's go ahead and add in our tree package. So now we have, and we're going to just note how it does bring in the linked list package by default because of how it does that nesting package system. Just drag it up into, or how do we do it again? Oh no, right. I just got to edit it. So refactor.
You just drag it to the top though. You should drag it to where the algo is.
Not just do move and just delete. Oh no, not that. Yeah, that nodes. I want nodes. I don't want linked list. That's it. When you're naming it, remove the linked list name. So when you do create a package and it asks for the name, just get rid of the linked list in the name first. Don't do linked list dot tree. Just do nodes tree. And I didn't realize I capitalized that one. That's fine. We'll do another. So what we'll do is we're going to actually bring in the node class here. We're going to update it. We're going to modify it and make it a little new. So we're going to actually, no, hold on. I have methods in there, don't I? No, I don't. Okay, good. Yep. So copy it, we'll paste it into here. Keep it node again, it's fine. Don't ask me to ask questions. So now again, so if we think about it again, if you remember correctly what the difference is between a linked list, if we look back quick, just think about it. The linked list was circle, arrow, circle, arrow, circle, arrow. A node, on the other hand, does this, arrow, arrow, right?
Tree, yeah.
Yep, sorry. Yeah, a tree, on the other hand, a tree's node has 2 arrows here and there. And so what do we need here? We need to change something up in our definition now. How do we change our definition to match that node?
Instead of just the singular next, we need something to distinguish the 2 branches, probably left or right.
Yep, exactly. We have something like that. So we do another node, and then we need to give it a name. Yeah, and it's just any sort of binary comparator, left, right, up, down, high, low. I wouldn't recommend doing 1 or 2. I guess you could do un, dos. So you can do uno, dos, because that's actually text, but you can do 1 or 2 in text, but I wouldn't recommend that. Yeah, but yes and no, left and right, up and down, high and low, anything like that can be used as your items, but the most primary item you see is, yes, left and right. That is the common you'll see whenever dealing with one of these. So that is our tree node. Now let's do a new Java class, tree. And again, I'll add it manually. Again, we'll start with our node integer head. So the symbol head right there again. And our no, that's supposed to be main class. Whoops. That and move that up. There. Hold on.
Oh, we just add a PSV on. Oh, and we put that in there. Okay.
All right. So the first thing we're going to build, and the very basic one, of course, is our add. I know that. So last time we did use the whole. What was it? We did the assert result kind of system where we did like test-driven development. This time we'll do it without the test-driven. So again, you see that difference in how we approach it. Instead of writing a test, we're just going to try to solve it without a test. And then we'll write just a printout later to see if it worked. So what we'll do here is going to do again, public void add node. We got again our node again. Now we'll do integer because that way we can do the stuff, the conditions later better. So node integer, comma, integer. Val.
And don't forget to name the node.
Thank you. Okay. And like before, we're actually going to return what? When we add a node, what do we actually want to return?
Returning the node, aren't we?
Well, we're going to return a node, but which node are we returning specifically?
Oh, head.
Yeah, so just make sure we're on the same page. same thing as before. Our add node is going to, again, return the head of the node of the whole tree. So it's going to return the head of the tree, just like before. All right. Nothing different there. This is still the same. So as before, our head is currently what?
That's null right now.
So again, if our tree hasn't been started yet, our tree's head is null. There is no tree yet. And so and this is where you'll start seeing some similarities in the previous one. We can start our add node the same way we did with our linked list. So you can simply do if head equal null. Ooh, I want to make sure this is set up right. Oh yeah, that's fine. Yeah. Return node. And just give it was like, wait, that constructor works. Again, remember last time how when we created this node, we don't set left and right, we just set the value. So the same constructor we used for the linked list can be used for the tree. We still don't set the left and right nodes. We want those to stay null. We don't initialize them. We don't set them. We keep them null. That tells us there is no node hanging off of that branch. That branch is an empty branch. If our head is equal to null, we return the new node. But now comes the next question. What do we do if there is a node? So now let's say we do the add node at 6. We'll start with 6. Got that. Initialized, that's fine. We know it's not, it's okay. So in this version of it, if I bring up my annotation there for some reason, not sure why, this is now set to 6. So now we get to say, okay, well now let's go ahead and do three.
Does head have a red underline on line 7?
Also, hold on. I keep forgetting this. What about line 7? What?
Does it have an error on line 7 under head?
It's letting us know that variable head might not be initialized. It's not necessarily an error.
Okay.
Or do I have to set it to null at the beginning? You know what? We'll just do that. Just make
I think you have to set it to just a new.
Right, because I just forgot. It's undefined, not null at beginning.
New
node. No, not new node.
No?
Null.
Oh, it just equals null? Okay.
Yeah, we don't have a tree yet, remember?
Okay.
Yeah, so it has to be null. If you give it any sort of node, we have a tree. All right, so we have that. We then have head, we pass it in. Right now head is always null, it says. Just true, we want that, that's fine. And whatever the result of this is, we return it. We know that the first run of this is gonna run, and we're gonna get our 6 node just like this. This is what it's gonna look like. We then wanna add the 3. And then we have to decide, well, how do we add the 3? Because we can't put the 3 here, the 6 is already there. If we run this code, we would replace the 6 and we would lose our 6. So now we need to add this 3 somewhere. And we now need to, so we could, without any rules, is there any restrictions to where we can put it? Technically. We can set restrictions on ourselves, but right now, out of the box, is there any restriction placed on us on where we can put it?
No.
All right, I can put it left or right, can't I? Right? Wherever I want. The question, of course, is that could be helpful later on when someone wants to look through my tree. If I'm just starting to add these nodes wherever I want, then we're going to run into a problem later when someone wants to scan this tree for data later. So if I just do 3 here, we'll do a 2 here, we'll do a 8 there, we'll do a 9 there, and a 10 here, and a 7 there, and
You'll have
a
to
1
traverse
here.
the whole tree just to find anything.
Exactly. If I needed to find out if the 8 exists in my code, I have to go down here, then back up over here. Nope, nope, nope. Over here, yep, found it. So I have to go through the whole node to find out where it is. And if I want to know if something doesn't exist, I have to search the entire tree to confirm that it doesn't exist. And this becomes no different than an array that is unsorted. No different than that. The downside, of course, is that this would most likely take up more memory because I would most likely need to do some sort of recursive system in order to go down the list and come back up to go down the other branches. So I would actually use up more memory than an array. So this is not great. And that's where the benefits of the binary tree comes into play. The way you use a binary tree effectively is by following a certain rule on what left and right mean. And that way, when you know that whenever a node is added, it's going to follow those rules. So then when you go to search for the item, you search and you'll ask certain questions on each node. What do you guys think our rule should be here? So I'm trying to add the 3 to the tree. Where should it go?
Should be less than and right should be greater than.
Greater than.
I like that. That makes sense, right? If it's smaller than the number here, we'll go to the left. If it's higher, we'll go to the right, right? So we'll add the 3 here. That's what we want to do. And let's say then we try to add a 9 to our system. We try to add the 9. We'd see the 6 here. Which way should we go?
Right.
I'll go over here, right? If we then add a 5 to the system, where would it go? So we go here. Where does the 5 go next?
Goes to the
Go to
left,
3.
Goes left, and then based on the 3, where should it go?
the right.
Right.
Exactly. And at first, it seems like, well, why wouldn't I just try to inject the 5 in here, right? You might think. That, again, takes memory requirements. That might take more memory to do. We don't know if the 3 is pointing at other stuff. And it could throw off our numbers. It could throw off our system. And so all we're saying is that it also adds it in the order it sees it. And that can help. That can be other information you can glean from. It's not always great information because you don't know how many items are on the right side or anything like that. But it can still be useful information to know that it was there at some point. Because now when we come in, we can then say, okay, well, I need to know if there is a 5 in this list. And so we go, okay, in that case, is the first node a 5?
No.
No, it's not. So that means that if the 5 did come into the tree, it came in after the 6. That's what this tells me, based on the logic of how I understand the rules of this tree work. If the node I'm looking at isn't the number I'm looking for, then the number, if it's in the tree, came in after this number. And so if the 5 came in after, which way would it go? Which way would it fall? We know it's going to fall to the left, right? Because it's less than. I look here, I see a 3. All right, well, that's not my number, which again, that means if the number was here, it would go to the right, right? Mm-hmm. So I go and then I find my number. If I'm looking for the number 1, I'm going to ask the same questions. Is this my number 1? No. Well, if the 1 came after the 6, it's going to go to the left. This is a 3. That's not my number. Well, if it's here, it came after the 3, it's going to go to the left. Oh, there's nothing there. The 1 was never added to the tree. I don't need to check this entire side on the right, do I? There could be a whole bunch of numbers here, but just by going through this logic, I can eliminate a bunch of items on this other side based on those rules. And that's one of the benefits you get from binary trees. You can search a little more effectively for information. So let's go ahead and now build out this logic. So clear my drawings. I don't think we need them. I need to add them back. I will. All right. So, ooh, I should have kept that actually. Dang it. Can I undo? Let's do that. Let's do this quick though. Select all this. I want to move this over here. I want to move it too far where it's over your guys' spaces, but I do want it here. So then I'll leave these numbers up. Oh yeah, no one confirmed for me. Do we know if the videos are still showing up or not?
No, they're not.
Yes. I could move them all the way to the right. But I'm not going for now. We don't need to. They're already there. All right. So let's say again, so yeah, we know right now we're adding 1 node, but if we were trying to add multiple nodes, let's say we're several nodes deep. So I need to add that 5 there. I need to do what with my tree?
You need to iterate, well, you have to traverse it, iterate through it just to know where you need to go.
What does that word tell me I might need? Don't answer, Jim. What does that statement tell me I might need?
A traveler.
Yeah, if I need to traverse my tree, I need a traveler, right? Travelers are great at traversing. They are great at traveling around stuff and they're great navigators. Which I will let everybody know, by the way, just for the clarification, that is the other type you might see. You might see one called a nav. That is another version of a traveler, another name for it. It is not used as commonly, but it is also another common item. So you have your traveler or your navigator or nav. So you have trav and nav. Those are the two types of travelers or navigators you'll see on a node-based system or structure. So just be aware that if you do look at one, you see the word nav, it stands for navigator. It's identical to trav. I'm more familiar with trav because I've seen it more, and it's also what I was taught with. So I'm passing traveler on to you guys. Yes, for me, my concept was like I pictured a traveler in the middle of the rainforest going from following instructions, going left to right. But then also because we know that if you try to access the value of a null node, that's you walking through the bushes and then falling off the edge of a cliff because you didn't look first. So that's kind of the concept. You need to look to see if there's a node there before you go. So it worked for me in my visuals. I don't know why I pictured a like tropical jungle for it and like an Indiana Jones type person, but whatever.
Because code is exciting, Cliff.
At least for me, it is.
I'm just thinking of Squid Games right now. Is it there? Is it not?
Maybe I should try. Maybe I should call my my traveler Magellan.
There you go. I'm just waiting for someone to call it Jones for Indiana Jones. Traveler Jones. But let's go ahead and we'll go ahead and create our new traveler now. So I'm going to node integer trav equals head. Again, even though we know that our head in Java doesn't get reassigned, it is passed by value, not by reference. Again, I want to make sure we're using this trav system because again, it's what you're going to see a lot in examples of navigation, examples of code, especially in other languages. So I want to make sure you guys are familiar with what you're going to see when you look this stuff up. So that's one of my main goals for this. All right, so we have that traveler head. Now we're going to be, and not only that, we still need to be able to return this head here when we're done. No matter where we go with the traveler, this needs to be returned. So if I do change this in order to navigate this tree, this one would be a problem. Later on, when I'm doing like the other ones, when I'm like finding a node and returning it or anything like that, then I could modify the head if I want. Trav is a very good policy to follow. It is the common syntax, the common way that people create these. So. All right, we have our traveler. We know that where we are, we can't put the node there. So now we have to decide, where do we go? To go. Right? Where are we going? What's the logic we want?
So if
Travis currently pointing at the 6.
Right. So if trav.val or value, excuse me. Trav.value is, I guess we'll check less than first, is less than val.
Got it. Yeah, that sounds right.
We're gonna say, well, do we know if we're at the bottom yet, or the
we do
the
not. We
right,
do not.
Okay. Do we have to do that? We have to do that first, I think.
Right. And so we do need to find out if we are where we need to be. So we need to first. So here we then do the if or check or null. So let's add some comments first. Check for null.
Sure.
If not null, what do we do?
Create a new node with the value of L.
If not null,
we descend
further.
We do that check again.
Travel. Right. Move our traveler down the node, right? So if 3's there, our travel's pointing at 6. If we go moving left and 3's there, we're not going to do anything. We're going to just move our traveler to point at 3. And then we're going to repeat the item. But yeah, travel and with null, what do we want to do? Like
what I just said.
Yeah. Add right?
Yes.
We do want to loop this. Now, normally we would have like a while statement. Like, does anyone have any idea what the while statement here was? We did do while before. It was trav.next
Next is
not equal to null. Does that work here?
No, it doesn't.
No,
because
and
we
I
have
can't really
two.
say left or right, right?
Right.
So this is where you start to see something called, or you're gonna start seeing this more often. All true.
Okay,
Well,
we'll have a breakout statement somewhere in the code.
Most commonly in this system, we're going to do what's called a breakout. Yeah, we're gonna eventually break out of the code at some way, shape, or form, or break out of the loop. At some point, though, if you do figure out that there is a conditional you can put here, then find it, then put it. What this does for me, a lot of times I may not know if there is or what the breakout or the conditional for the end of the loop is. I may not be in my head yet. And so what I'm going to do is like, you know what, screw it. While true, I'm going to put at the bottom here a break just to make sure that if I do accidentally click the run button to test it, I don't break the code. I don't create an infinite loop. And then what I need to do is make sure that some way I either break out of the conditions naturally or I figure out what the conditional is and I put it here. So at some point I do want to figure that out, that all routes have a break. And I know that sometime at some point somewhere I will eventually get out of this naturally, that there is a, what is the term for that concept? That ends a loop that will otherwise end into a break into a infinite loop. We talked about this on Monday, not Monday, was it Monday? Today's Monday. No, today's Tuesday, right? Yeah. Was it yesterday we did this? Thursday. Was that?
You're talking about a base case?
That, yes, thank you. That was Thursday, yes. Brain broke, yeah, base case. A while true is a potential infinite loop. And so just like how a recursion system is a potential infinite loop, any sort of potential infinite system needs a base case that causes it to break out or to end. And so we just need to make sure that at some point we create either the base case for our while loop or the conditional that we need naturally. And in most while loops, you can actually consider your conditional to be the base case. So now we can do if trav is less than value, we can now check for null. If trav dot left equal to null. What do we want to do here? So this is if,
go to the right.
Double check the conditions here. So if trav dot left is null. Look at these two. Which one are we going to use?
Well,
line 27 or line 28?
Right, not trav dot left based on the condition.
Value is less than val. So 3 versus 6. Oh no, if trav, you're right. Okay. Yep. Right. if this is less than our new value, which might be a little confusing, we might want to do value less than trav dot value. But again, if you guys get this, because now we see that our arrow isn't matching. So I prefer to do this. The reason for that is now my less than symbol will match the direction of my tree. Make sense?
Yeah, that makes sense.
Yeah.
Let's see if I get that right. I always get these backwards.
Yep. If our
Dyslexia
new value,
and yeah,
yeah, what this is saying is if our new value is less than our current node's value, we want to go to the left of the node. So
yeah,
this
usually
matches
like
up
to
with
put
our
whatever is the parameter first when comparing values.
It can be. I tend to let, again, the how it sounds and how it words and how the logic inside matches. I try to match as much as I can to make sure that it's intuitive. So yeah, I tend to lead with the parameter, but if I notice that this might make more sense, I'll gladly switch it. I'm very much a fan of readability and functionality over stickler for rules that aren't necessary. I'm only doing this one because, yeah, I like the fact that the less than symbol now matches my direction that I'm traveling. It's literally telling us, hey, go left.
Done.
So now what do we do here? I want to hear some other voices. Matt and Mike have definitely been the loudest today, I feel like. I hear more voices. What's that?
Yeah, add the node.
Beautiful, right? We do this one. If null, add the node. So that means trav.left equal to new, not less, left, new node, val. Yeah, I don't need to actually put the number there because it's, oh, here I do, but there I don't because it's going to set it to the value of this guy. It's going to intuitively know what node to create. Forgot about that. Cool. So this one doesn't need it. Yeah. You can leave it there if it's there. Don't worry about clearing it, but you don't need it because it determines the T based on what you send it. The value, the type of the parameter sets the type of the node because we didn't make those the same. So we got that. And then once we do this, is there anything else we need to do in this method? What's the ultimate goal of this method?
Add a node to the tree.
Add a node to the tree, right? As of this line, have we done that?
Oh, yes.
Yeah, so
add a second node to the tree we've done, yes.
Yeah. So would it be safe to say we're done?
No. Well,
why? What else
yeah,
do?
that one, yeah, that would be yes for the left.
Yeah. So what do we need to do? So we could end the method here by just doing a return what?
Head.
Yeah. We can just end the method here. We don't have to worry about breaking out of our loop or breaking out anything or doing anything after the loop. Once we do what the main goal of the method is, leave. That's something that a lot of people tend to forget a lot of times. All you're trying to do in any method is do what the method wants. And as soon as you do it, return right away. Don't worry about trying to clean things up all the time, because these variables we created will get cleaned up naturally through the garbage collection system. So we don't have to do any sort of cleanup. We don't have to exit out of the loop. This will exit out of the loop for us. This will clean everything up for us. So definitely be aware of that. That's a very useful tool to be able to take advantage of. Once you realize I've done what I came here to do, get out of the method, leave, stop hanging around. Don't overcomplicate it. So now, so now that we've done a return head there, if we're on line 129, what does that tell us? What can we logically say about the code if we hit line 29? It's that logic deductive reasoning. Because of this if statement, if my code hits line 29, what does that tell us?
We're going to the right.
Why?
Because value is larger than 6.
Not that, no, not yet. So all this will tell us is something based on this if statement, not this one. That's after this curly bracket. And here, we just did the opposite of what this if statement is doing. This if statement must be false if we hit this line. In order for this line to be hit, this if statement has to be false, and this if statement must be true still. So this statement is still true, but this one is false. So what do we know as of this line?
It's not null.
What is it?
Trav.left.
Right, we now know that trav.left is not null. We know that there's a node there. That's our intuitive discussion. We don't need to do a else if statement here to say else if trav.left is not null. That's that concept here where we know something without explicitly stating it. We don't need that else or else if statement to clarify that trav.left is not equal to null. We just know that because the only other option for this is not null. If this was true, we would have returned. We wouldn't have hit this line. We can only hit this line if trav.left is not null. And that's that concept of deductive reasoning. So we know as of this line, trav.left null. So now we can do lull. We do what Travis said, which is move. So trav equals trav.left. Once we move, what do we want to check again? So once we move to left, what do we want to do? So we're here. We know there's a node here. We know there's a node here. So we don't need to do this check, right?
Correct.
Yeah, we already know that. So what checks do I want to do here? Do I want to do this check again and just this check?
No.
I want to do everything again, right?
Right.
So where do I want to go? Back where? What line?
22.
Yeah, I would say 19 personally, because I don't like 22 is the if statement. I mean, I want to do this again. So, and 21 is just a comment.
Oh, so we have to go back up to the top.
We want to start a new loop, right? We want to start a new iteration of the loop.
So that would be a continue.
Ah, good. Yes. Remember, when I'm done with a iteration of a loop and I want to start the next iteration of the loop, that's what continue does.
I used an else on this, and it said that I didn't need to continue if I did that. So I'm trying to make sure I'm on the same page.
Probably right now it'll probably tell us we don't need it because we haven't done anything else yet. So right now it's going to hit that. I'm not sure why I would tell you that. Break Yeah, see, it's telling us now. Yeah, we don't need it right now because we don't have any other options of code it could run into. So what we're going to do now, though, is we're going to do this. So if our value is less than trap.value, we do want to do another check. So there's technically, you want to think about it, how many options can we run into here?
2.
That's it?
Oh, wait, no, there's equal. That's right.
Right, I could get equal, which in that case, we don't want to add that node, right? We just want to do nothing. Yeah. Most of the time, binary trees are meant to be sets. Most linked lists and binary trees are meant to be sets. They don't have to be, but there is usually a common practice of that is to be sets. If you don't want your binary tree to be a set, you just have to decide which direction gets equal and make sure you stick to that. So are we going to do less than or equal to or greater than or equal to? You have to pick one and you have to stick to that. Mm-hmm. So that's why 9 times out of 10, binary trees are considered sets because there's no intuitive way to decide should my equal go left or right, right? Yeah, so a bit annoying. So yeah. What you could do in this case is make your node more complex and do add to the node something called t-value and then public int quantity and count how many times that node has been added. And then every time you remove the node, you just remove 1 from the quantity. Unless it's 0, then you remove the node altogether. So you, again, one thing to keep in mind, nodes can be complex. You're not restricted to a single value. You can have a ton of values in it, more data, constant data you can add. You can make child nodes that have more data and more information. So always be aware of that. You can definitely make that's most likely what you would do in this case. You would make a child node or a child class that inherits from this one that has additional data. Now let's go ahead and do the other direction, which is greater than. So if greater than trap.value. And the niceness here is that it gives us that greater than symbol or what direction?
Right.
Right.
Yeah. So now we're looking to the right if this is true. So again, what are we going to do here?
Same thing as we did up there.
Yeah.
Pretty much just with right instead of left, right?
Mm-hmm.
So we can we'll go ahead and just grab this. It's one time where
right instead
it's
of left.
different enough to copy paste. And we'll just change all our lefts to right. And then at some point though, if we're not less than and if we're not greater than, what does that mean? If somehow our code hits line 43, what does that mean?
Must be equal.
Has to be, right? Because if it was if the value was less than and the traveler, the next node was null, we would have added it and then returned, we would have ended the method. If it wasn't null, we would have moved and then gone back to the top. And so in this if statement, there's no way to get to once we enter this if statement, we're not getting out of it, right? So this if statement, once we go inside of this if statement, we're going back, we're either leaving the function, going back to the top of the loop. The same can be said for this if statement too, right? Once we enter this if statement, we're either leaving the function or we're going back to the top. So the only way for us to hit this line of code is if val is equal to traps. I don't need to do the if statement. And that's that thing to keep in mind. You don't always have to add an if statement. It is sometimes considered an explicit logic, an explicit reasoning or explicit logic, or sorry, explicit condition. There we go. You don't need an explicit condition at all times. This is a hidden one. This is a non-explicit condition. There we go. Forgot the word non. It's a non-explicit condition. This line right here. We don't need to clarify if val is equal to trap.value. Because it's given that if the two other if statements fail. All we know here is that if the node is the same, because we want our binary tree to be a set, we're just going to go ahead and do turn head.
Oh. So put that where the break goes. Got it.
We're not going to add a new node. We're not going to add 2 6s to the system because that's going to be confusing for our system right now. For this version of the binary tree, our binary tree is going to be a binary tree set. Only unique values. Make sense?
Yes.
Cool. All right. That's our adder. Go ahead and do the 2 here. We're just going to go ahead and add 3, 6. Let's do head node 9. Add node 5. Let's do an S out. Head value out. Dot left value.
I put in Slack the binary tree creator that that Elaine and I found like last year that we like to put out.
Interesting.
Mm.
You guys can take a look at that later. Kind of cool. Let's see. Back to what we were doing. I want to get this done because we're already at 9:22. So let's finish this up. Then S out. Left. Dot. Just to make it interesting, we're going to do this actually instead of doing, we'll do very quick blank. All right, so what we should see here is our 6, 3 space 9 space 5, if this all worked correctly. Make sense?
Mm-hmm.
Cool. See if it worked.
Oh,
and I just ran my linked list. Sorry, hold on.
I did too.
Yep.
Like, where did this come from?
It's like, I don't remember all that. And there we go. 3, 6, 9, and 3 to the 5. Even though the 5 is under the 9, I could add some tabbings to make it move over a little more, but this is good enough for now.
Nice.
At least get it looking decent. So we have our node. Later on, what we're going to do is we're going to go ahead and do a find method. We're also going to do a interesting display methods. We're going to do a couple display types that will be interesting to look into. So we'll probably do the display linear, which we just do 6, 3, then we just go down the left, down the right, back up, left, right. We just go down, and just as we find them, we print them in a certain order. We'll also do though, we print what's called a level version, which we'll print the first row first, then we'll print the second row next, and then the third row, fourth row, fifth row, like that. And you'll see how just by printing a different way, how we need to change stuff up, and even how we might need to add one of our other data structures in order to do that. And so that one, where we print the level version, where we do a binary tree level print, we are going to need another data structure to do that. And that's where, again, we're going to start seeing how simple systems can get more complicated, but how using our building blocks and our toolkits that we have can make something that seems complicated easier to do. So that'll be probably next Tuesday we do that, because again, I want you guys to spend the week digging into that Udemy course. So dig into that. Keep practicing with your linked lists. I'm going to leave that open for you guys. So that's the main thing why I didn't give you too much of the Udemy course to get into. I know some of you still haven't finished them all. So keep working on the linked lists, get that working. If you have those done, just dig into this Udemy course then. Go in deep on it. That and your personal projects, of course. So yeah, the main thing that you got to remind yourself, you have cost analysis you have to run. You have your personal projects, you have your Spring Boot lessons to go through, you have your algorithms, and now this Udemy course. You want to spend a little bit of time on each, definitely, but the thing is, how much time do you spend on each overall? Do you spend more on one or the other? One of the ways to evaluate that, of course, is where are you weakest? Maybe focus on that a little extra than you normally would if you were equal in all skills. Some things are definitely more important because they are more important to your hiring, but you just want to gauge and weigh all those factors and figure out what's going to best help you get the job. What do you think you need most for the interview? Do you need your projects more? Do you need your algorithm skills up to par? Do you need your Spring Boot skills up to par? What do you need? Do you need your vocabulary up to par? So do more of the vocabulary stuff, learn those terms of art, research those things, whatever you need. All right.
Mhm.
Cool. Any questions?
Just because I cloned your repository, and make sure you push the changes, because I'll probably take
Right
another
now.
look at that at work tomorrow. And what we did today, just now.
On its way. All good.
Thank you, sir.
And I'll get both of it, make sure that I'll double check, make sure the React video is up. I feel like I didn't upload it. So I'll go double check that and get that up as well. So I'll upload the video from yesterday and today's video as soon as I can. All right. Like I said, if you guys do decide to do like a class-wide kind of meetup tomorrow for algorithms or anything, let me know. I can give you guys a Zoom meeting so that way you don't have to worry about the 40-minute time limit. Just ping me on Slack. Make sure to use the @ symbol so I don't miss it. So @ me so I can come in and pop that in. I'll even put a @ channel so whenever you guys finalize your time frame, people will at least know, hey, @ channel, here's when the class is meeting up. So if anyone wants to join and wants to help out or learn or just observe, they can. Sound good?
Mhm.
Cool. Can we get like a little study session? Awesome. I'll see everybody on Thursday for more React.
That's it.
Cool. Good night, everyone.
Have a good night, everyone.
Everybody.
Good night.
Take care.
Guys.